One of the dirty tricks that people have used over the years with Green's theorem is to use it to calculate area. Namely, if you have some vector field and its scalar curl, del q del x del y minus del p del x is equal to 1, then Green's theorem says that if I take an integral around the boundary of that region of this vector field, then that's the same as the double integral over the inside of 1, and that's the area of the region. So this means that by doing a line integral calculation around the boundary, we get an area calculation for the inside. So here are some example vector fields that satisfy this property that we've written down here. All right, so this leads to something called the surveyor's formula, which goes along with the third of those vector fields. The integral of minus y over 2 dx plus x over 2 dy around the boundary calculates area. And by kind of evaluating that out, you can get a formula for calculating area of shapes in 2D with linear sides. That's a little bit surprising. So here's a four-sided shape that has corners at the points 0, 0, 2, 0, 3, 4, and 1, 5. If you haven't seen the shoelace formula before, here's how you do it. You write down those points, their x and y coordinates, in a kind of vertical array like this. And when you get to the end, you wrap around to the beginning like so. Then what you do is you multiply out along little diagonals like this. So 0 times 0 gives us 0, 2 times 4 gives us 8, 3 times 5 gives us 15, and 1 times 5 gives us 0. Then you multiply along the opposite diagonals. 0 times 2 is equal to 0, 0 times 3 is equal to 0, 4 times 1 is equal to 4, and 5 times 0 is equal to 0. And then what we do is we add up these and subtract those. So we get 0 plus 8 plus 15 plus 0 minus 0 minus 0 minus 4 minus 0. So in this case, we get the number 8 plus 15 minus 4, which is 19. That tells us that the area of this shape is 19. And this doesn't involve any trig. This doesn't involve breaking things into triangles. This doesn't involve base times height over 2 or anything like that. It just, oh, I'm sorry, I'm supposed to divide the answer by 2, and I forgot. So 19 over 2 is the area of the shape. This doesn't involve base times height over 2. It just kind of cleanly gives us the area, no matter what the complexity of the shape are. And if we accidentally wrote it down in the wrong order, if we accidentally went clockwise around the boundary, it would give us the negative instead of positive. So that's extremely handy for figuring out areas of shapes in 2D. And as another application, there's a device called a planimeter, which is very old school, but it's a physical, piece of machinery where you put it down on a table and it has a little swing arm. So it's got two kind of angled arms, one swings around on the other, and a little wheel on the end of that swing arm. And as you draw a shape on the table, the little wheel moves if the motion of movement is perpendicular to the arm, and it doesn't move if the movement is parallel to the arm. And as it does, that little wheel kind of clicks around and measures, and it tells you at the end of the day what the total area is if you draw around the outside boundary. So that's extremely kind of surprising that you can get a device that does that type of measurement, and whoever invented that was a lot more clever than I am.